Things in space that would actually give you. Superpowers space is not just empty darkness. It's filled with extreme environments where physics pushes reality to its limits. In some of these places, conditions are so intense that they would fundamentally alter the human body in ways that feel almost like superpowers or instant destruction. From crushing gravity to time distortion and radiation fields that rewrite biology, today we're exploring what would happen if a human was exposed to the most extreme objects in the universe. Cosmic radiation, the force that mutates life. Somewhere in deep space, far beyond the reach of Earth's atmosphere, entire stars are dying in explosions so violent that they can briefly outshine billions of other stars combined, releasing colossal waves of energy into the universe and launching invisible particles across interstellar space at speeds so extreme that some of them travel incredibly close to the speed of light itself. These particles cross unimaginable distances for millions of years without stopping, cutting through galaxies, magnetic fields, clouds of gas, and empty darkness before finally slamming into planets, moons, spacecraft, and living organisms. Right now, as you are watching this video, countless high-energy particles from distant parts of the universe are moving through your body, through your walls, through the Earth beneath you. And most people never notice because cosmic radiation is completely invisible, silent, and impossible for human senses to detect naturally. But even though you cannot see it, cosmic radiation is one of the most powerful forces constantly interacting with life on Earth, and the deeper scientists investigate it, the more disturbing and fascinating it becomes. This is because cosmic radiation is not just ordinary energy floating through space. Some of these particles carry so much power that they can damage human DNA instantly, alter cells, trigger mutations, and release more energy than anything humans can produce naturally on Earth. Others are so unbelievably energetic that scientists still struggle to explain how the universe creates them in the first place. The universe is essentially firing microscopic bullets through space at almost unimaginable speeds, and Earth has been sitting inside this storm for billions of years. What makes this even more important is the fact that radiation does not simply destroy life. Under certain conditions, radiation can also change life. Evolution itself depends on genetic change. Without mutation, life never adapts, species never evolve, and intelligent organisms like humans never appear. Every animal, every plant, every living organism on Earth exists because countless mutations accumulated across billions of years, slowly altering DNA generation after generation. Cosmic radiation may have played a role in that process from the very beginning. And this creates an incredible question. If life on Earth evolved under the relatively protected conditions of this planet, then what would happen to life evolving somewhere else in the universe under far harsher radiation? What would happen on worlds orbiting violent stars that constantly bombard their planets with deadly energy? What would happen on planets with weak magnetic fields where cosmic radiation reaches the surface far more easily? Could living things evolve extraordinary biological defenses? Could they become resistant to radiation itself? Could evolution eventually create organisms capable of surviving conditions that would kill humans within minutes? When most people hear the word superpowers, they think about comic books, fantasy, or science fiction. But nature already creates abilities that seem unbelievable. Some organisms can survive radiation levels thousands of times stronger than what humans can tolerate. Some can repair shattered DNA. Some can survive direct exposure to outer space. And scientists are beginning to realize that the universe may naturally push evolution toward extreme adaptations wherever survival becomes difficult enough. Cosmic radiation understanding begins in the early 20th century with a physicist named Victor Hess, whose experiment would completely change humanity's understanding of the universe. At the time, scientists already knew radiation existed because radioactive elements on Earth naturally released energy. But researchers believed most background radiation came from the ground itself. The assumption seemed logical. Since radioactive materials existed in Earth's crust, radiation levels should decrease the farther someone moved away from the surface. Victor Hess wanted to test that theory directly. In 1912, he climbed into a hydrogen balloon carrying delicate scientific instruments capable of measuring radiation levels. The higher he travelled into the atmosphere, the more dangerous the mission became. Temperatures dropped sharply. Oxygen levels became dangerously low. Balloon travel itself was still extremely risky at that time, but Hess continued climbing because he wanted clear measurements from higher altitudes. At first, the experiment appeared to confirm existing theories. Radiation levels dropped slightly as the balloon rose above the surface. But then something happened that completely shocked him. Instead of continuing to decrease, the radiation levels suddenly began increasing. The higher Hess travelled, the stronger the radiation became. This result made no sense according to the accepted explanation. If the radiation was coming mainly from Earth, then it should continue weakening with altitude. Instead, the exact opposite happened. Something from above Earth was producing enormous amounts of radiation. That meant the source was space itself. Victor Hess had just discovered cosmic rays, one of the most important discoveries in modern physics. His experiment revealed that Earth was constantly being bombarded by high-energy particles arriving from deep space. Humanity suddenly understood that the universe was not quiet or empty. Space was active, violent, and continuously interacting with our planet in ways nobody had fully realized before. Hess later received the Nobel Prize for the discovery, but scientists still did not fully understand what cosmic rays actually were. For years, researchers debated their nature because the particles behaved unlike anything previously studied. Eventually, scientists discovered that cosmic rays were not ordinary rays at all. Most cosmic rays are actually subatomic particles moving through space at extraordinary speeds. The majority are protons, the positively charged particles found inside atomic nuclei, while others include heavier atomic nuclei stripped of electrons, along with electrons and other exotic particles created during extreme cosmic events. These particles travel with enormous energy, sometimes reaching velocities incredibly close to the speed of light, making them some of the fastest moving objects in the universe. The real mystery, however, was not simply what cosmic rays were, but where they came from. Scientists eventually discovered that some cosmic rays originate from supernova explosions, the catastrophic deaths of massive stars. When enormous stars finally run out of fuel, gravity crushes their cores inward with such overwhelming force that the star collapses violently before exploding outward in a blast powerful enough to temporarily outshine entire galaxies. During this explosion, gigantic shock waves race through space at incredible speeds, accelerating particles to enormous energies and throwing them across the cosmos like debris from a celestial bomb. Other cosmic rays appear to come from quasars, which are some of the brightest and most energetic objects ever discovered in the universe. Quasars form around supermassive black holes located at the centers of distant galaxies. These black holes consume huge amounts of gas, dust, and surrounding matter, creating massive disks of superheated material spiraling inward at extraordinary speeds. As matter falls toward the black hole, magnetic fields twist violently and release colossal jets of energy stretching across millions of light years. Inside these environments, particles can be accelerated to energies so extreme that even modern human technology cannot reproduce them. Some cosmic radiation may also come from active galactic nuclei, where gigantic black holes, millions or even billions of times more massive than the Sun, dominate the centers of galaxies. These regions are among the most violent environments known to science. Gravity becomes so intense that matter heats to incredible temperatures, while powerful magnetic fields and relativistic jets blast particles across intergalactic space. Then there are neutron star collisions, which are among the most violent events in existence. Neutron stars themselves are already extraordinary because they are the collapsed remnants of massive stars compressed so densely that a single teaspoon of neutron star material would weigh billions of tons. When two neutron stars spiral into each other and collide, the resulting explosion releases unimaginable amounts of energy. Space-time itself ripples outward in gravitational waves while radiation floods across the universe. Scientists now believe these collisions produce many of the heaviest elements in existence, including gold and platinum, while also generating some of the most energetic particles ever observed. What makes cosmic rays even more incredible is the sheer distance they travel. Some of the particles reaching Earth today may have started their journeys millions of years ago, long before human civilization existed. Some may have begun traveling through space before dinosaurs walked the planet. Others may have crossed entire galaxies before finally colliding with Earth's atmosphere, and when they arrive, they hit with astonishing force. Fortunately for life on Earth, the atmosphere acts like a giant protective shield. Most cosmic rays collide with atoms high in the atmosphere before reaching the ground. These collisions create enormous particle showers, producing cascades of secondary particles that spread downward across the planet. Without Earth's atmosphere and magnetic field, radiation levels at the surface would be vastly more dangerous. Mars provides a perfect example of this problem. Unlike Earth, Mars has a thin atmosphere and lacks a strong global magnetic field, leaving the surface exposed to far more cosmic radiation. This is one of the greatest challenges facing future human missions to Mars, because astronauts spending long periods there could suffer serious biological damage. Cosmic radiation can break DNA strands, damage brain tissue, increase cancer risk, weaken organs, and interfere with the body's natural repair system. But not all cosmic rays are equal. Some are so powerful that scientists initially thought their instruments had malfunctioned when they detected them. In 1991, researchers studying cosmic radiation recorded one of the most astonishing particles ever discovered. The event became famous as the "Oh my God" particle, because the scientists analyzing the data were genuinely stunned by the energy involved. The particle was detected by an observatory in Utah called the Fly's Eye experiment. At first, researchers struggled to believe the reading because the particle carried an absurd amount of energy for something so microscopic. The energy level reached approximately 320 quintillion electron volts, making it one of the most energetic particles ever observed. To make this understandable, scientists compared its energy to something familiar. This single subatomic particle carried roughly the same amount of kinetic energy as a baseball traveling at high speed. That comparison sounds impossible because atoms and subatomic particles are unimaginably tiny. Yet somehow, the universe accelerated one microscopic particle until it carried energy comparable to a physical object humans could throw with their hands. Even today, scientists still debate how such particles are created. Some researchers suspect they originate near supermassive black holes. Others think they may come from powerful galactic jets or unknown extreme cosmic processes. But no explanation fully solves the mystery. The discovery revealed something deeply important about the universe. Nature is capable of producing energies far beyond anything humans can currently achieve. Even the Large Hadron Collider, the most powerful particle accelerator ever built by humanity, cannot match the energy levels of the strongest cosmic rays. Space itself remains the ultimate particle accelerator. But the true significance of cosmic radiation is not simply the enormous energy involved. What matters most is what radiation does when it interacts with living tissue. The human body is built from atoms arranged in incredibly precise biological structures. Cells rely on delicate chemical reactions and electrical signals to function properly, while DNA contains the genetic instructions controlling everything from growth to repair to reproduction. Radiation interferes directly with these systems. When high-energy radiation strikes atoms inside the body, it can knock electrons away from molecules in a process called ionization. This damages cellular structures and creates unstable chemical reactions capable of harming proteins, membranes, and DNA itself. Radiation can break DNA strands apart completely, preventing cells from functioning normally. Sometimes damaged cells die immediately. Sometimes they malfunction. Sometimes they become cancerous. But occasionally, cells survive and repair themselves imperfectly. These imperfections become mutations. Most mutations are either harmful or neutral, but evolution depends on rare mutations that provide survival advantages. Over enormous periods of time, these genetic changes accumulate, gradually reshaping species generation after generation. Without mutation, evolution would stop entirely. Cosmic radiation has almost certainly contributed to this process throughout Earth's history. Every organism on this planet evolved while constantly exposed to at least small amounts of radiation from space. Scientists even suspect that nearby supernova explosions may have increased cosmic radiation reaching Earth during certain periods in the distant past, potentially influencing evolutionary patterns and environmental conditions. What becomes truly fascinating is the fact that some organisms on Earth have evolved extraordinary resistance to radiation already. One of the most famous examples is the tardigrade, a microscopic animal often called the water bear because of its appearance under a microscope. Despite looking tiny and harmless, tardigrades are among the toughest organisms ever discovered. These creatures can survive freezing temperatures near absolute zero, extreme heat, crushing pressure, dehydration, and even direct exposure to outer space. Most astonishing of all, they can survive radiation levels that would instantly kill humans many thousands of times over. Scientists discovered that tardigrades possess specialized proteins capable of protecting DNA from radiation damage. Their cells also contain powerful repair mechanisms that can rebuild damaged genetic material with remarkable efficiency. When conditions become too hostile, tardigrades can enter a suspended state where their metabolism nearly stops completely, allowing them to survive environments that should be fatal to complex life. In experiments conducted outside spacecraft, tardigrades exposed directly to the vacuum and radiation of space still survived. That sounds fictional, but it is completely real. Another extraordinary example is a bacterium called Deinococcus radiodurans, one of the most radiation-resistant organisms ever discovered. This bacterium can survive radiation doses that completely destroy most known forms of life. Scientists found that even after its DNA is shattered into fragments by intense radiation, the bacterium can reconstruct its genome and continue living. Imagine if humans possessed repair systems like that. Imagine cells capable of fixing radiation damage almost immediately. Imagine biological defenses strong enough to prevent most cancers before they develop. Imagine bodies capable of surviving environmental conditions currently considered lethal. Researchers are now studying these organisms carefully because understanding their biology could help improve medicine, protect astronauts during deep space travel, and reveal how life might evolve on hostile planets elsewhere in the universe. And that possibility becomes even more interesting when scientists consider worlds far more dangerous than Earth. Some planets orbit extremely active stars that release constant radiation storms. Others may lack magnetic fields entirely, exposing their surfaces directly to cosmic bombardment. Any life surviving there would need extraordinary biological adaptations. Evolution on such worlds could favor thick radiation-resistant tissues, enhanced DNA repair systems, altered cellular chemistry, or entirely different biological structures more resistant to damage. Compared to those organisms, humans might appear incredibly fragile. What makes this even more interesting is that humans are already beginning to experience biological changes caused by space itself. One of the most important experiments involved NASA astronaut Scott Kelly and his identical twin brother, Mark Kelly. Scott spent nearly a year aboard the International Space Station, while scientists carefully monitored changes occurring inside his body and compared them to his twin remaining on Earth. The results fascinated researchers because they revealed that space environments genuinely alter human biology at the genetic level. Scientists observed changes in gene expression, meaning certain genes became more or less active during spaceflight. His immune system showed noticeable alterations. Researchers also detected changes involving telomeres, the protective caps located at the ends of chromosomes and often associated with aging. Unexpectedly, Scott Kelly's telomeres became longer during his mission. Longer telomeres are sometimes linked to slower biological aging, which surprised scientists studying the effects of space travel. Although many of these changes reversed after returning to Earth, the experiment demonstrated something extremely important. The environment beyond Earth actively changes the human body. Space is not simply empty darkness surrounding astronauts. It is an entirely different biological environment filled with radiation, microgravity, altered pressure, isolation, and physical stress capable of reshaping how the body functions. Radiation plays a major role in these changes. Beyond Earth's magnetic field, astronauts face far greater exposure to cosmic rays and solar radiation. Future missions to Mars may expose humans to dangerous radiation levels for months or even years. Scientists worry this could damage the nervous system, impair memory, weaken the immune system, increase cancer risk, and accelerate cellular degeneration. But evolution operates through environmental pressure. When organisms face new dangers over long enough periods, adaptation sometimes follows. If humans eventually live in space permanently, future generations may slowly evolve improved resistance to radiation and other cosmic dangers. And if genetic engineering advances far enough, humans may not even need to wait for natural evolution. Modern technologies like CRISPR already allow scientists to edit DNA directly. Researchers are studying radiation-resistant organisms for genes that might one day help protect astronauts during long-duration missions. The line between natural biology and engineered adaptation is beginning to blur. And this is where the idea of scientifically plausible superpowers becomes genuinely fascinating. Extreme radiation resistance already exists in nature. Advanced cellular repair already exists. Enhanced survival abilities already exist. The universe may not produce comic book superheroes, but it absolutely produces organisms with capabilities humans would consider extraordinary. A future human engineered for survival in harsh cosmic environments might possess biological traits that seem almost superhuman compared to people living today. Such humans might repair DNA damage rapidly before disease develops. Their cells could resist radiation exposure far more effectively. Their tissues might tolerate extreme environments impossible for unmodified humans to survive. Their immune systems could detect and destroy damaged cells with incredible efficiency. Compared to present-day humans, they would appear fundamentally transformed. And this may ultimately be necessary for survival because the universe is not designed for fragile life. Space is filled with lethal radiation, violent explosions, collapsing stars, magnetic storms, and particles accelerated to unimaginable speeds. Earth protects humanity from most of these dangers, but beyond our atmosphere lies an environment that constantly attacks biological tissue. Any civilization hoping to spread across the stars may eventually need to adapt physically to survive cosmic radiation itself, because radiation is only one of the forces shaping life in the universe. Gravity may be even more powerful. Somewhere out there are planets with gravitational forces so intense they could crush the human body into permanent weakness, while other worlds possess gravity so weak that movement itself would feel almost supernatural compared to Earth. On such planets, evolution would push life toward entirely different forms, creating organisms shaped by environments far more extreme than anything humans evolved to handle. Because radiation can rewrite DNA, but gravity can reshape entire species. Supergravity, how other worlds could create superhumans. Gravity is one of the most powerful forces in the universe, yet it is also one of the strangest, because humans experience it every second of their lives without ever truly noticing how much control it has over the body, the planet, the oceans, the atmosphere, and even time itself. Every movement you make right now is controlled by gravity. Every step, every heartbeat, every drop of blood moving through your veins is happening under the constant pull of Earth beneath your feet. Human muscles evolved because of gravity. Human bones became dense because of gravity. The shape of the skeleton, the strength of the spine, the way blood circulates through the body, and even the way humans walk are all direct responses to living on a world with Earth's exact gravitational pull. If Earth's gravity was stronger, humans would look completely different. If gravity were weaker, the human body would also change dramatically over generations. And somewhere out there in the universe, there are planets where gravity is so powerful that life would evolve into something far denser, tougher, and stronger than anything on Earth, while other worlds may create organisms capable of leaping enormous distances, surviving crushing acceleration, or moving with what would appear to humans as impossible agility. For centuries, gravity was deeply mysterious because nobody truly understood what caused objects to fall toward Earth, or why planets stayed in orbit around the Sun. Ancient civilizations saw gravity simply as a natural behavior of matter, but in the 17th century, English scientist Isaac Newton transformed humanity's understanding forever. According to the famous story, Newton became fascinated by gravity after seeing an apple fall from a tree, leading him to ask a question that would reshape science completely. Why do objects always fall downward? Why does the moon not drift away into space? Why do planets remain locked in orbit around stars? Newton realized these events were connected by the same invisible force. He proposed that every object with mass attracts every other object with mass, and the greater the mass, the stronger the gravitational pull becomes. His equations explained the movement of planets with astonishing accuracy and became one of the foundations of classical physics. But centuries later, scientists discovered that Newton's explanation was incomplete because gravity turned out to be even stranger than anyone imagined. In the early 20th century, Albert Einstein completely changed humanity's understanding of gravity through his theory of general relativity. Einstein proposed that gravity was not simply an invisible force pulling objects together. Instead, massive objects actually bend space and time themselves. According to Einstein, space is not empty nothingness. Space and time form a connected fabric called space-time, and massive objects warp this fabric around them. Planets orbit stars not because they are being pulled by invisible ropes, but because they are moving through curved space-time created by the star's enormous mass. A common way scientists explain this idea is by imagining a heavy bowling ball placed on a stretched rubber sheet. The bowling ball creates a deep curve in the sheet, and smaller objects rolling nearby naturally move toward it. In a similar way, stars bend space-time around themselves, causing planets to follow curved paths we call orbits. Earth itself bends space-time as well, which is why humans remain attached to the planet instead of floating away into space. This understanding completely transformed physics because gravity was no longer just a force. It became a distortion of reality itself. What makes gravity even more fascinating is that it changes dramatically across the universe depending on the size and density of worlds. Earth has a gravity humans evolved to handle comfortably, but other planets can be vastly different. Some worlds have much weaker gravity, while others possess crushing gravitational forces that would make movement incredibly difficult for human beings. In recent decades, astronomers have discovered thousands of planets outside the solar system, known as exoplanets. And some of these worlds are unlike anything humans imagine possible. Among the most fascinating are planets called super-Earths. These are rocky planets larger and heavier than Earth, but smaller than giant gas planets like Jupiter. Some super-Earths may have gravity 2, 3, or even 4 times stronger than Earth's. One famous example is Kepler-22b, discovered by NASA's Kepler Space Telescope. Although scientists are still studying its exact composition, the planet is believed to be significantly larger than Earth and possibly located within the habitable zone of its star, where temperatures might allow liquid water to exist. Another fascinating world is Gliese 667cc, a super-Earth orbiting within the habitable zone of a red dwarf star roughly 23 light-years away. Scientists estimate that the gravity on such planets could be far stronger than Earth's gravity depending on their mass and density. To understand how powerful this becomes, imagine your body suddenly weighing 3 times more than it does right now. Every movement would feel exhausting. Standing up would require far greater effort. Running would become extremely difficult. Jumping might barely be possible at all. The heart would need to pump blood against far greater force, and the skeleton would experience enormous stress constantly. Humans raised on Earth would struggle terribly on such worlds, but life evolving there from the beginning would adapt over millions of years. Evolution always responds to environmental pressure. On a high-gravity planet, organisms with weak bones or inefficient muscles would struggle to survive, while creatures with denser skeletons, more powerful muscles, and stronger cardiovascular systems would have major advantages. Over time, life on these planets could become extraordinarily tough. Creatures evolving under intense gravity would likely develop compact but extremely muscular bodies, because tall and thin structures would collapse more easily under stronger gravitational force. Bones would become thicker and denser to support greater weight. Muscles would contain far more strength relative to body size because every movement would require overcoming heavier gravitational pull. The cardiovascular system would also change dramatically because the heart would need to work much harder to circulate blood throughout the body. Blood vessels might become stronger and more efficient, while lungs could evolve to process oxygen more effectively to support powerful muscles operating under constant strain. Compared to humans, intelligent life from a high-gravity world might appear unbelievably strong. Imagine a being born on a planet with 3 times Earth's gravity visiting Earth for the first time. Their body would already be adapted to functioning under extreme weight and resistance. On Earth, they would suddenly feel incredibly light. Movements requiring effort on their homeworld would become easy. Jumping higher, lifting heavier objects, and moving faster would all become possible simply because Earth's gravity would feel weak compared to what their bodies evolved for. To humans, such creatures might seem almost superhuman. And strangely enough, humans already experience smaller versions of this effect through physical training and high-gravity exposure. Fighter pilots provide a real example of how gravity affects the body. During sharp turns and rapid acceleration, pilots experience intense G-forces, meaning gravity temporarily becomes several times stronger than normal Earth gravity. At high G-forces, blood is pulled downward so strongly that the brain may not receive enough oxygen, causing pilots to lose vision or even black out completely. Modern fighter pilots train extensively to survive these conditions. They wear special G-suits designed to squeeze the legs and abdomen to prevent blood from draining away from the brain. They also learn muscle techniques that help maintain circulation during extreme acceleration. These conditions demonstrate how dangerous increased gravity can become even for short periods. Scientists have also conducted centrifuge experiments where humans experience artificial gravity far beyond normal levels. In giant rotating machines, subjects are exposed to intense forces that place enormous stress on muscles, bones, and organs. Over time, the body begins adapting to some of these stresses. Bone itself is highly responsive to mechanical pressure. The skeleton constantly rebuilds itself based on physical demands. Weightlifting increases bone density because bones respond to stress by becoming stronger. Astronauts in low gravity lose bone density because their skeletons no longer experience enough mechanical load. Gravity is constantly shaping the human body. This means gravity is not simply an external force acting on life. It directly influences evolution and biological structure. Nature already provides remarkable examples of how environmental conditions create extraordinary strength. Ants, for example, can lift many times their own body weight because small creatures experience physics differently than larger animals. Their tiny size allows muscle strength to scale more efficiently relative to body mass. Gorillas possess enormous muscular density compared to humans because their evolutionary history favored tremendous physical power. But evolution always involves trade-offs. Creatures evolving under high gravity might become extremely strong but less agile. Their bodies could require enormous energy consumption to function. Compact structures might limit speed or flexibility. Massive bones and muscles would increase survival under gravity, but may create disadvantages in other environments. Still, if such organisms arrived on a lower gravity world like Earth, those same adaptations could appear astonishing. The opposite effect occurs in low gravity environments. Mars has only about 38% of Earth's gravity. The Moon has just 1/6. Humans visiting these environments experience movement very differently. Astronauts on the Moon during the Apollo missions could leap high above the surface with ease, because gravity pulled them downward far less strongly than on Earth. On Mars, humans would weigh far less than they do here. Running and jumping would become easier, while lifting heavy objects would require less effort. A person capable of jumping 1 meter on Earth could potentially jump far higher on Mars. Over generations, however, low gravity could reshape human biology in dramatic ways. If humans permanently lived on Mars for centuries, natural selection and environmental adaptation might gradually produce thinner skeletons, because heavy bones would no longer be necessary. Muscles might shrink because less force is required for movement. Human height could potentially increase because weaker gravity places less stress on the spine and skeletal structure. Future Martian humans might become taller, lighter, and more agile than Earth humans. Imagine children born and raised for generations in low gravity. Their bodies would develop entirely differently from humans on Earth. Returning to Earth might feel crushingly heavy to them, while on Mars they could move with incredible speed and jumping ability. To Earth observers, they might appear almost superhuman in low-gravity environments, but gravity becomes truly terrifying near the most extreme objects in the universe. Black holes contain gravitational forces so immense that they completely distort space and time. These objects form when massive stars collapse under their own gravity, compressing enormous amounts of mass into incredibly tiny regions of space. The gravity becomes so powerful that not even light can escape once it crosses a boundary called the event horizon. Near black holes, gravity behaves in ways that seem almost unreal. One of the strangest effects is called tidal force. Gravity weakens with distance, meaning the closer you are to a massive object, the stronger gravity becomes. Near a black hole, this difference becomes extreme. If a person approached a black hole feet first, gravity pulling on the feet would become far stronger than gravity pulling on the head. The result would be catastrophic. The body would stretch vertically while compressing horizontally in a horrifying process scientists call spaghettification. The closer someone moved toward the black hole, the stronger this stretching would become, until eventually the body would be torn apart at the atomic level. This sounds like science fiction, but it is real physics predicted by Einstein's equations. Yet black holes also reveal something even stranger about gravity. Gravity affects time itself. According to general relativity, time moves more slowly in stronger gravitational fields. Near massive objects, clocks literally run slower compared to clocks farther away. This effect, called gravitational time dilation, has been experimentally confirmed many times. The stronger the gravity, the slower time passes. Near Earth, the effect is tiny but measurable. Near neutron stars or black holes, the effect becomes enormous. This means a person spending time near an extremely massive object could experience time differently compared to someone far away. Hours for one observer might equal years for another, depending on the gravitational conditions involved. This is not fantasy. It is real physics. Modern satellites already prove it every day. GPS satellites orbiting Earth experience slightly different gravitational conditions than people on the ground. Because gravity is weaker farther from Earth, time passes slightly faster for the satellites. Their onboard clocks drift relative to clocks on Earth, and scientists must constantly correct these differences for GPS systems to function accurately. Without accounting for Einstein's relativity, GPS navigation would quickly become inaccurate. Gravity literally changes time. Near extremely massive objects, the effect becomes dramatic enough to resemble time travel into the future. A person orbiting close to a black hole for a short period could theoretically return to find that far more time passed elsewhere in the universe. This creates one of the strangest scientifically real superpower effects imaginable. Slower aging through relativistic time dilation. Of course, surviving near such environments would be extraordinarily difficult because radiation, tidal forces and extreme gravity would make black holes incredibly dangerous. But the underlying physics is real. The deeper scientists study gravity, the more they realize it is not simply a force pulling objects downward. Gravity shapes biology, evolution, movement, energy, and even the flow of time itself. On high-gravity worlds, evolution could produce compact beings with enormous strength, dense bones, and powerful cardiovascular systems capable of surviving conditions humans would find unbearable. On low-gravity planets, organisms could evolve incredible agility, extreme jumping ability, and skeletal structures optimized for lighter environments. Near massive cosmic objects, gravity itself begins altering time in ways that seem almost impossible. And many of the abilities humans associate with fictional superpowers are actually connected to real gravitational physics. Superstrength could emerge naturally from evolution on high-gravity worlds. Enhanced endurance could develop through cardiovascular adaptation to constant physical stress. Extreme jumping ability becomes realistic in low-gravity environments like Mars or the Moon. Even slower aging through relativistic effects exists within real physics under extreme gravity. The universe may never create superheroes exactly like comic books imagine them, but the environments scattered across space absolutely have the power to reshape living organisms into forms that would appear extraordinary to humans on Earth. Because gravity is not just something life survives, gravity is something life evolves around. Magnetars, the most dangerous magnets in the universe. Somewhere in the darkness of the universe, there are dead stars so violent, so extreme, and so unbelievably powerful that if one passed too close to Earth, it could tear apart the technology of our civilization without ever physically touching the planet. These objects are not black holes, quasars, or exploding stars. They are something even stranger. They are magnetars, the most magnetic objects ever discovered in the known universe. And the forces surrounding them are so extreme that normal human language almost fails to describe what they can actually do. A magnetar is not simply a star with a strong magnetic field. It is a collapsed stellar corpse with magnetic power so immense that it can distort atoms themselves, release catastrophic bursts of radiation across space, interfere with the structure of matter, and unleash more energy in 1 second than the Sun produces in hundreds of thousands of years. Scientists studying these objects quickly realize that magnetars exist in a completely different category of physics compared to almost everything humans experience on Earth, because the conditions surrounding them push matter, energy, and magnetism to limits rarely seen anywhere else in the cosmos. To understand magnetars properly, it is important to first understand neutron stars, because magnetars are actually a rare and extreme type of neutron star. When massive stars reach the end of their lives, the process becomes unimaginably violent. For millions of years, a giant star survives because of a balance between gravity pulling inward and nuclear fusion pushing outward. Deep inside the star's core, atoms fuse together under enormous pressure, releasing colossal amounts of energy that hold the star up against its own gravity. But eventually, the star runs out of fuel. Fusion slows down, the outward pressure weakens, and when that happens, gravity wins instantly. The collapse happens with terrifying speed. The outer layers of the star rush inward at millions of kilometers per hour, while the core compresses so violently that protons and electrons are forced together, creating neutrons packed tightly against one another. The star collapses so dramatically that something larger than the Sun can become compressed into an object barely 20 kilometers wide. Imagine crushing a star into the size of a city. The density becomes almost impossible to comprehend. A single teaspoon of neutron star material would weigh billions of tons on Earth. Matter inside neutron stars is packed so tightly that atoms themselves are essentially crushed apart. Then comes the explosion. The collapsing star rebounds violently in a supernova blast powerful enough to outshine entire galaxies for short periods of time. Shockwaves tear through space. Radiation floods outward. Heavy elements are scattered across the cosmos. And at the center of the explosion, the collapsed core remains behind as a neutron star. Most neutron stars are already among the strangest objects in existence. They spin at incredible speeds, sometimes rotating dozens or even hundreds of times every second, while releasing beams of radiation into space like cosmic lighthouses. But in very rare cases, something even more extreme happens during the collapse. If the original star had the right conditions, the magnetic field trapped inside the collapsing core becomes compressed to absurd levels. Since magnetic energy becomes concentrated into an incredibly tiny space during the collapse, the field strength increases dramatically beyond anything humans normally encounter. The result is a magnetar. Scientists believe magnetars possess magnetic fields thousands of times stronger than ordinary neutron stars and trillions of times stronger than Earth's magnetic field. To understand how ridiculous this becomes, consider the fact that Earth's magnetic field already plays a major role in protecting life. It shields the planet from solar radiation, guides compasses, and shapes the movement of charged particles around Earth. Yet compared to a magnetar, Earth's magnetic field is almost nothing. The magnetic field of a magnetar is so powerful that it can affect matter from enormous distances. Scientists often explain this using one famous comparison. If a magnetar passed halfway between Earth and the Moon, its magnetic field could erase every credit card on Earth instantly. That sounds dramatic enough, but the reality is far more terrifying because magnetars do not simply affect electronics. Their magnetic fields are strong enough to alter the structure of atoms themselves. The discovery of magnetars came gradually as astronomers detected mysterious bursts of high-energy radiation coming from space during the late 20th century. Certain neutron stars appeared to behave differently from ordinary pulsars. They emitted intense X-rays and gamma rays far stronger than expected, and their behaviour suggested magnetic forces far beyond normal astrophysical models. Scientists eventually realised they were dealing with an entirely new class of object. The term magnetar was introduced during the 1990s as researchers developed theories explaining these extraordinary observations. What shocked scientists most was not just the existence of magnetars, but the sheer scale of their magnetic fields. The strongest magnetic fields humans can produce in laboratories are incredibly tiny compared to those surrounding magnetars. Even the most advanced electromagnets on Earth become insignificant in comparison. Near the surface of a magnetar, the magnetic field can reach around 1 quadrillion Gauss. Earth's magnetic field, by comparison, measures roughly half a Gauss. The difference is so extreme that it almost becomes meaningless to compare them directly. Near a magnetar, magnetism becomes one of the dominant forces controlling reality itself. On Earth, atoms behave according to relatively stable electromagnetic interactions. Electrons move around atomic nuclei in predictable patterns called electron clouds. Chemistry depends on these structures. Biology depends on chemistry. Human bodies depend on stable atomic interactions. But near a magnetar, the magnetic field becomes so intense that it begins distorting these electron clouds directly. Atoms themselves become stretched and warped. Matter no longer behaves normally. Chemical bonds can change under the influence of such extreme magnetism. The very shape of atoms becomes altered because the magnetic field overwhelms the natural behavior of electrons. Scientists believe that near the surface of a magnetar, ordinary matter may become elongated into strange cylindrical forms due to the crushing dominance of magnetic forces. This is not simply strong magnetism in the everyday sense humans understand from refrigerators or magnets sticking to metal. This is magnetism operating at cosmic extremes where the laws of matter begin behaving differently. Even light itself can be affected. According to quantum physics, extremely strong magnetic fields may alter the vacuum of space itself. Under such conditions, empty space can behave strangely as virtual particles constantly appear and disappear. Near a magnetar, the magnetic field may become powerful enough to influence how light travels through the vacuum around the star, changing polarization and creating bizarre optical effects predicted by quantum electrodynamics. These are some of the most extreme physical environments known in the universe. And magnetars are not stable. The crust of a neutron star is incredibly dense and rigid. But the magnetic forces inside a magnetar become so powerful that they twist and stress the crust continuously. Over time, the pressure builds to catastrophic levels until the crust suddenly cracks in violent ruptures called starquakes. A starquake on a magnetar releases staggering amounts of energy. To understand how powerful this becomes, imagine earthquakes on Earth but magnified to cosmic scales. During a starquake, the magnetic field rearranges violently, releasing huge bursts of X-rays and gamma rays into space. These explosions are among the most energetic events in the galaxy. One of the most famous examples occurred on December 27, 2004, when a magnetar known as SGR 1806-20 unleashed a giant flare so powerful that it temporarily affected Earth despite being located about 50,000 light-years away. Think about that distance for a moment. The radiation travelled across half the galaxy and still managed to impact Earth's atmosphere. The flare released more energy in a fraction of a second than the Sun emits in hundreds of thousands of years. When the radiation reached Earth, it partially ionized the upper atmosphere and disrupted instruments on satellites. Some spacecraft detected sudden spikes of radiation so powerful that sensors were overwhelmed. Scientists later realized this was the brightest extrasolar event ever recorded on Earth in modern times. And this magnetar was unimaginably far away. If such a flare occurred closer to Earth, the consequences could become catastrophic. A nearby magneto eruption could damage satellites, disrupt communication systems, interfere with power grids, and flood Earth with dangerous radiation. Fortunately, no known magnetars close enough to pose immediate danger currently threaten the solar system, but the event demonstrated just how powerful these objects truly are. The deeper scientists study magnetars, the more they realize these objects push physics toward extreme boundaries rarely encountered elsewhere. Their magnetic fields dominate matter so completely that normal physical intuition stops working. Conditions near a magnetar cannot really be compared to anything humans experience naturally, because there is simply nothing remotely similar on Earth. But strangely enough, magnetism already plays an important role inside living organisms. The human brain itself operates partly through electrical activity. Neurons communicate using electrochemical signals traveling through vast networks inside the nervous system. Every thought, memory, movement, and sensation depends on tiny electrical pulses moving between brain cells. Since electricity and magnetism are deeply connected forces, magnetic fields can influence neural activity under certain conditions. Scientists have studied this relationship for decades. One important technology is called transcranial magnetic stimulation, often shortened to TMS. This technique uses magnetic fields to influence activity in specific regions of the brain. By placing electromagnetic coils near the skull, researchers can generate magnetic pulses capable of affecting neurons beneath the surface. The results can be remarkable. TMS has been used experimentally to alter perception, temporarily disrupt speech, stimulate movement, and even influence mood or memory processing. Scientists discovered that carefully targeted magnetic stimulation can change how certain brain regions function for short periods of time. Researchers continue studying whether these methods might help treat neurological conditions such as depression, chronic pain, or certain cognitive disorders. What makes this fascinating is that it demonstrates something extremely important. Magnetic fields can interact with human cognition. Not at the absurd levels surrounding magnetars, of course, because those conditions would destroy human tissue instantly. But the connection between magnetism and neural function is very real. And humans are not the only organisms influenced by magnetic fields. Many animals appear capable of sensing Earth's magnetic field naturally through a phenomenon called magnetoreception. Birds are one of the most famous examples. Migratory birds travel thousands of kilometers across continents and oceans with astonishing accuracy, and evidence suggests many species use Earth's magnetic field as part of their navigation system. Sea turtles also appear capable of detecting magnetic information during migration. Certain fish, insects, and even bacteria possess biological systems sensitive to magnetic fields. Scientists still do not fully understand exactly how magnetoreception works in all species, but some theories involve specialized proteins called cryptochromes inside cells, while others suggest tiny magnetic crystals called magnetite may help organisms detect magnetic orientation. This means some living creatures already possess a form of natural electromagnetic awareness. To humans, such abilities might seem almost like superpowers. Imagine perceiving invisible magnetic fields directly. Imagine sensing direction instinctively, without maps or compasses. Imagine detecting electromagnetic changes in the environment the way birds may detect Earth's magnetic structure during migration. Nature already demonstrates that biology can interact with magnetism in remarkable ways. And scientists continue exploring whether stronger or more refined forms of magnetic interaction could influence perception further. Research into magnetic stimulation has produced intriguing experiments involving memory, sensory processing, and awareness. Some studies suggest magnetic fields may influence visual perception under certain conditions. Others investigate whether magnetic stimulation can enhance learning, focus, or reaction speed temporarily by affecting neural circuits in the brain. There have even been experiments where researchers use magnetic stimulation to interfere with specific cognitive functions deliberately. In some cases, stimulating certain brain regions can temporarily alter decision-making, emotional processing, or sensory interpretation. This does not mean scientists are creating mind-control technology like science fiction movies portray, but it does reveal something deeply important about the brain. Human cognition is partly electrical, and anything electrical can potentially interact with magnetism. The connection between biology, electricity, and magnetism becomes even more fascinating when considering the broader universe, because every nervous system on Earth evolved under relatively weak magnetic conditions. Earth's magnetic field protects life from radiation and shapes certain animal behaviors, but it is tiny compared to the environment surrounding neutron stars and magnetars. If life somehow evolved in environments with stronger magnetic conditions, could biology adapt in unusual ways? Scientists do not know, but evolution constantly responds to environmental pressure. Life on Earth already evolved electric organs in creatures like electric eels, capable of generating strong electrical discharges. Some sharks can detect tiny electrical signals produced by prey hidden beneath sand. Magnetoreception already exists in several species. The building blocks for electromagnetic sensitivity are already present in biology, and this is where the concept of scientifically plausible superpowers becomes genuinely interesting. Enhanced sensory perception based on magnetic awareness is not impossible in principle, because nature already demonstrates partial versions of it. Organisms with highly advanced magnetoreception might navigate perfectly across huge distances, sense electromagnetic disturbances, or detect environmental changes invisible to ordinary humans. Future technologies could potentially expand human interaction with electromagnetic information even further. Brain-computer interfaces, neural implants, and advanced magnetic stimulation research are gradually increasing humanity's ability to interact directly with electrical activity inside the nervous system. Compared to modern humans, future modified humans with enhanced electromagnetic sensing abilities might appear extraordinary, and magnetars themselves remain among the greatest reminders of how extreme the universe truly is. These dead stars represent physics pushed toward violent limits, where matter bends under impossible magnetic pressure, radiation erupts across galaxies, and atomic structure itself becomes distorted. They reveal that the cosmos contains environments so powerful that even the normal behavior of atoms can change completely. Near a magnetar, human technology becomes meaningless. Electronics would fail instantly. Atoms distort. Radiation floods space. Matter itself behaves differently. And yet these objects are real. Somewhere in the galaxy right now, magnetars are spinning silently in darkness, carrying magnetic fields so powerful that they can reshape the structure of matter and unleash bursts of energy capable of crossing tens of thousands of light years. The universe is filled with forces far beyond ordinary human experience, and magnetars may be some of the most terrifying examples of all. Dark matter, the invisible stuff passing through your body. Right now, at this exact moment, something invisible is moving through your body, through the walls around you, through the entire Earth beneath your feet, and scientists believe it has been doing this for billions of years without human beings ever noticing. It does not glow, reflect light, produce visible color, or behave like ordinary matter, which is why nobody on Earth has ever directly seen it with their eyes. Yet despite being invisible, scientists now believe this mysterious substance outweighs every star, planet, moon, asteroid, cloud of gas, black hole, and galaxy humans can actually observe in the universe. Entire galaxies appear trapped inside enormous halos of this hidden material. Giant clusters of galaxies move as though they are submerged inside colossal oceans of invisible mass. Light itself bends around it. Gravity responds to it. The structure of the universe depends on it. And without it, scientists believe galaxies should not even exist in the stable forms humans observe today. This strange, invisible substance is called dark matter, and it remains one of the biggest mysteries in modern science because researchers know it exists, they know it surrounds us constantly, and they know it controls huge portions of the cosmos, but they still do not know exactly what it is. The story of dark matter begins in the early 20th century, when astronomers started realizing that the universe was behaving in ways that did not make sense according to visible matter alone. One of the most important figures in this discovery was Swiss astronomer Fritz Zwicky, a brilliant but controversial scientist known for his aggressive personality and unusual ideas. In the 1930s, Zwicky began studying massive groups of galaxies called galaxy clusters, focusing particularly on the Coma cluster, which contains thousands of galaxies bound together by gravity. At the time, astronomers assumed they could estimate the mass of a galaxy cluster by observing the visible matter inside it, including stars, gas, and glowing material. But when Zwicky calculated how fast the galaxies inside the Coma cluster were moving, something deeply strange appeared in the data. The galaxies were traveling so quickly that the visible matter alone should not have produced enough gravity to hold the cluster together. According to normal physics, the galaxies should have flown apart into space long ago, but they had not. Something invisible appeared to be creating enormous additional gravity inside the cluster. Zwicky realized that the universe seemed to contain huge amounts of hidden mass that telescopes could not see. He called this unseen material dark matter, though at the time many scientists ignored the idea because it sounded too strange, and the evidence was still limited. For decades, dark matter remained one of astronomy's most controversial concepts, because nobody knew whether the missing mass problem was caused by invisible matter, incorrect measurements, or gaps in human understanding of gravity itself. Then the mystery became impossible to ignore. In the 1970s, astronomers studying galaxy rotation discovered another enormous problem. One of the most important researchers involved was Vera Rubin, whose observations helped completely transform modern cosmology. Rubin studied how stars moved inside galaxies, expecting to see behavior similar to planets orbiting the Sun. In the solar system, planets farther from the Sun move more slowly because gravity weakens with distance. Scientists expected galaxies to behave similarly, meaning stars near the outer edges should orbit much more slowly than stars near the center, where most visible matter exists. But that is not what happened. Instead, stars far from galactic centers were moving much faster than they should have been according to the visible mass present in the galaxies. The outer regions appeared to contain enormous amounts of hidden gravity. Once again, the universe seemed filled with invisible matter humans could not detect directly. This became known as the galaxy rotation problem, and it changed astronomy forever because the evidence kept appearing everywhere scientists looked. Galaxies rotated too fast. Galaxy clusters stayed together when they should have broken apart. Large cosmic structures behaved as though they were embedded inside gigantic invisible gravitational frameworks. The conclusion became increasingly difficult to avoid. Most of the matter in the universe was invisible. What makes dark matter so bizarre is that scientists cannot observe it using ordinary light. Everything humans normally see in space becomes visible because it interacts with electromagnetic radiation. Stars shine because they emit light. Planets reflect light. Gas clouds glow under radiation. Human eyes, cameras, and telescopes all depend on electromagnetic interactions to observe the universe. Dark matter appears completely different because it does not interact normally with light at all. It neither emits nor reflects detectable electromagnetic radiation, making it effectively invisible. Yet gravity reveals its presence constantly. Galaxies behave as though enormous invisible halos surround them. Galaxy clusters contain vastly more gravity than visible matter can explain. Even the largest structures in the universe appear shaped by dark matter distributions stretching across billions of light years. Scientists still do not know exactly what dark matter is, but researchers have developed several major theories trying to explain its nature. One possibility involves hypothetical particles called WIMPs, short for weakly interacting massive particles. These particles would possess mass, allowing them to create gravity, but they would interact extremely weakly with ordinary matter and light, making them incredibly difficult to detect. According to many theories, enormous numbers of WIMPs could fill the universe while passing almost completely unnoticed through normal matter. Another possibility involves axions, extremely tiny hypothetical particles originally proposed to solve problems in quantum physics. Axions would be incredibly light and difficult to detect directly, but huge numbers of them could collectively account for dark matter throughout the universe. Scientists have also explored the idea of MACHOs, or massive astrophysical compact halo objects, which include things like black holes, dead stars, or other dim objects difficult to observe directly. However, evidence now suggests MACHOs alone probably cannot explain all dark matter because the missing mass appears far too large and widespread. Then there are sterile neutrinos, hypothetical particles related to ordinary neutrinos, but interacting even more weakly with normal matter. Neutrinos themselves are already incredibly strange because trillions pass through your body every second without interacting significantly. Sterile neutrinos would be even harder to detect. The deeper scientists investigate dark matter, the stranger the mystery becomes because every answer creates more questions. Researchers know dark matter must exist because gravity repeatedly reveals its effects, but they still do not know which theory, if any, fully explains it. One of the strongest pieces of evidence for dark matter comes from something called gravitational lensing, an effect predicted by Albert Einstein through general relativity. According to Einstein's theory, gravity bends space-time itself, meaning massive objects can actually bend the path of light traveling nearby. Scientists observe this effect constantly in space. When light from distant galaxies passes near massive objects, the light bends and distorts, creating stretched images, arcs, or magnified cosmic structures. By studying gravitational lensing carefully, astronomers can map where mass exists in space, even if that mass is invisible. And what they discovered was astonishing. In many galaxy clusters, most of the mass revealed through gravitational lensing does not match the visible matter present. Huge invisible structures appear surrounding galaxies and clusters like gigantic hidden skeletons shaping the cosmos. One of the most famous examples is the Bullet Cluster, where two galaxy clusters collided in deep space. During the collision, ordinary matter such as gas clouds slowed down and interacted violently, but most of the gravitational mass appeared to pass straight through the collision unaffected. Scientists studying the event realized the invisible mass behaved differently from ordinary matter, providing some of the strongest evidence ever observed for dark matter existing as a separate physical component of the universe. Another major clue comes from the cosmic microwave background, often called the afterglow of the Big Bang. This faint radiation fills the entire universe and represents ancient light left over from the early cosmos shortly after the universe began. By studying tiny fluctuations inside this radiation, scientists can estimate how matter was distributed during the universe's infancy. The results revealed something extraordinary. Ordinary matter makes up only a small fraction of the universe. Dark matter appears to outweigh visible matter by a huge margin. Everything humans can see, including stars, planets, galaxies, dust clouds, oceans, animals, and human bodies, represents only a tiny percentage of the total matter believed to exist in the cosmos. Most of reality is invisible, and this invisible material is everywhere. Dark matter does not exist only in distant galaxies far away from Earth. Scientists believe enormous amounts of it surround the Milky Way right now, in a vast halo extending far beyond the visible stars of the galaxy. Earth moves through this dark matter continuously as the solar system orbits the galactic center. That means dark matter is passing through Earth constantly, and through you. Right now, countless dark matter particles may be moving through your body every second without leaving obvious traces, because they interact so weakly with ordinary matter. Unlike normal particles, which collide constantly with atoms inside your body, dark matter appears capable of passing through entire planets almost unaffected. This idea sounds unbelievable because humans instinctively think invisible things passing through solid matter belong in science fiction. But according to current theories, this may already be happening continuously across the universe. Scientists have spent decades trying to detect dark matter directly, leading to some of the most advanced and isolated experiments ever constructed. Since dark matter interacts so weakly with ordinary matter, detecting it requires incredibly sensitive equipment protected from interference by radiation and other particles. Many dark matter experiments are built deep underground beneath mountains or inside mines, because Earth itself acts like a giant shield, blocking unwanted cosmic radiation that could interfere with measurements. One major example involves xenon detectors, enormous tanks filled with ultra-pure liquid xenon designed to detect the tiniest possible interactions between dark matter particles and ordinary atoms. These detectors are often placed far underground, where background radiation becomes much lower. Scientists monitor them constantly, searching for incredibly rare signals that might indicate a dark matter particle collided with an atomic nucleus. The level of sensitivity involved is extraordinary because researchers are trying to detect interactions so small they may occur only a few times per year or even less frequently. Experiments like Xeno-NT, Luex Zeppelin, and Pandarx represent humanity's attempt to observe one of the universe's greatest mysteries directly. Massive underground laboratories have been constructed in places like Italy, China, Canada, and the United States, buried beneath rock layers specifically to isolate detectors from interference. Scientists hide these experiments underground for a very important reason. Earth's surface is constantly bombarded by cosmic rays and background radiation that can create false signals inside detectors. Deep underground, much of this interference disappears, allowing researchers to search more carefully for possible dark matter interactions. So far, dark matter remains frustratingly elusive. Scientists have detected many strange signals over the years, but no experiment has yet provided universally accepted proof of direct dark matter detection. Still, the search continues because the gravitational evidence remains overwhelming, and the possibility of eventually interacting with dark matter raises extraordinary questions. Could humans ever manipulate dark matter technologically? Right now, the answer remains completely unknown because scientists still do not fully understand its nature. If dark matter barely interacts with ordinary matter except through gravity, building technology capable of controlling it could become incredibly difficult. However, throughout history, humans repeatedly discovered ways to manipulate forces once thought unreachable. Electricity once seemed mysterious. Radio waves were invisible and unknown until technology revealed them. Quantum physics transformed understanding of matter itself. Dark matter may eventually become another frontier of discovery. Some theoretical ideas suggest advanced civilizations might one day harness dark matter indirectly through gravitational effects or unknown interactions not yet discovered. Others speculate dark matter could possess entirely new forms of physics beyond the standard model currently describing known particles. There are even speculative discussions about whether biological systems could ever evolve sensitivity to dark matter, though no evidence currently supports this idea. Since dark matter interacts so weakly with ordinary matter, such biological interaction would likely require entirely unknown mechanisms. Still, nature repeatedly surprises scientists. Animals evolve senses humans once considered impossible. Sharks detect electrical fields, birds navigate using Earth's magnetism. Some organisms perceive ultraviolet light or infrared radiation invisible to human eyes. Human perception evolved only for survival on Earth, not for understanding every force in the universe. If future technologies or biological modifications ever allowed humans to detect dark matter indirectly, the result could appear almost supernatural from a modern perspective. Imagine perceiving invisible gravitational structures surrounding galaxies, or sensing hidden matter flowing through space. Compared to ordinary human senses, such abilities would seem extraordinary, and dark matter may connect to even larger mysteries about the universe itself. Scientists now believe ordinary visible matter represents only a tiny fraction of total cosmic reality. Dark matter appears to outweigh visible matter significantly, while another mysterious phenomenon called dark energy may dominate the universe even further by driving cosmic expansion itself. This means humanity currently understands only a small portion of the cosmos. Most matter is invisible. Most large-scale structure depends on hidden forces humans still struggle to explain. Galaxies themselves may have formed because dark matter provided the gravitational framework allowing ordinary matter to gather into stars and planets after the Big Bang. Without dark matter, the universe might look completely different. The deeper scientists investigate reality, the clearer it becomes that human senses reveal only a tiny slice of existence. Human eyes evolved to detect a narrow band of visible light. Human hearing captures only limited sound frequencies. Even the solid world humans experience directly may represent only a small, visible layer floating inside a much larger, invisible cosmic structure dominated by forces and matter humans cannot naturally perceive. Dark matter represents one of the clearest examples of this hidden universe, because scientists know something enormous surrounds them constantly while remaining almost completely invisible. And perhaps the strangest part of all is that this invisible material may be moving through you right now, passing silently through every atom in your body while the universe carries both Earth and the Milky Way through gigantic oceans of unseen matter stretching across the cosmos. Neutrino powers, ghost particles with unlimited penetration. Neutrinos are among the most mysterious particles ever discovered in physics because they behave in a way that seems almost impossible compared to everyday matter on Earth, passing through planets, stars, and entire galaxies with almost no interaction. And yet they are produced in enormous numbers inside the most violent and energetic places in the universe. These particles are so small and so weakly interacting that for decades scientists struggled even to prove they existed. And even now, despite powerful modern detectors and advanced technology, they remain extremely difficult to study. What makes neutrinos especially fascinating is that they are constantly flowing through everything around you, including your body, without you ever noticing or feeling them. And this flow is happening on such a massive scale that at any given moment, trillions upon trillions of neutrinos are moving through every human being on Earth, making them one of the most abundant yet invisible forms of matter in the universe. Their ability to pass through almost anything without being stopped or absorbed gives them a kind of ghost particle behavior that challenges normal intuition, because unlike atoms or photons of light that interact frequently with matter, neutrinos mostly ignore everything they pass through, making them unique messengers from the deepest and most extreme environments in space. The discovery of neutrinos began with a major problem in nuclear physics during the early 20th century, when scientists studying radioactive decay noticed something strange and confusing happening in certain reactions. because when atomic nuclei broke apart, the energy and momentum before and after the decay did not seem to match perfectly, as if something invisible was carrying away a portion of the energy. This inconsistency became a serious puzzle for physicists because it appeared to violate the conservation laws of energy and momentum, which are fundamental principles in physics, stating that energy cannot simply disappear or appear without explanation. To solve this mystery, physicist Wolfgang Pauli proposed the existence of an unknown neutral particle that carried away the missing energy during nuclear decay. And although Pauli himself was unsure at first whether such a particle could ever be detected, he introduced it as what he famously called a desperate remedy to explain the missing energy problem. This hypothetical particle was later named the neutrino, and it would take decades before scientists were finally able to confirm its existence experimentally, proving that Pauli's idea was correct and that an entirely new type of particle existed in nature that had been completely invisible to detection methods available at the time. Neutrinos are now known to be extremely small, nearly massless particles that carry no electric charge, which means they do not interact with electromagnetic forces in the way that electrons or protons do. And this lack of electric charge is one of the main reasons they are so difficult to detect. Because they are electrically neutral, neutrinos do not respond to magnetic fields, do not stick to atoms, and do not interact through normal electromagnetic attraction or repulsion, allowing them to pass straight through ordinary matter almost as if it were empty space. In addition to this, neutrinos have extremely weak interactions with the strong nuclear force, meaning they rarely collide with atomic nuclei, and the combination of these properties allows them to travel through enormous amounts of matter without being stopped or deflected. Even though neutrinos are incredibly small and difficult to detect, they are not completely without mass, and modern physics has confirmed that they possess a tiny but non-zero mass, which slightly changes how they behave over long distances in space. One of the most astonishing facts about neutrinos is that they are constantly streaming through the universe in massive numbers, produced in some of the most energetic and extreme environments known to science, including the cores of stars, exploding supernova, and even the early moments of the Big Bang. The Sun alone produces an enormous number of neutrinos every second through nuclear fusion reactions happening deep in its core, where hydrogen atoms are being fused into helium under extreme pressure and temperature, releasing energy in the form of light, heat, and neutrinos. These solar neutrinos travel outward from the Sun's core at nearly the speed of light and reach Earth continuously, passing through the planet and everything on its surface without being significantly affected. At any given moment, trillions of solar neutrinos are passing through your body without any sensation or interaction that you can detect, meaning that human beings are constantly immersed in a stream of particles coming directly from the interior of the Sun. Even more extreme sources of neutrinos exist in the universe, because when massive stars explode in supernova events, they release enormous bursts of neutrinos that carry away a large portion of the explosion's total energy, and these supernova neutrinos can pass through entire galaxies without being stopped. During a supernova, the collapsing core of the star becomes so dense that neutrinos are produced in vast quantities as matter is compressed and transformed under extreme conditions. And these particles escape the star's interior long before light can escape, making neutrinos some of the earliest signals from stellar explosions that can reach distant observers. Because they interact so weakly with matter, neutrinos are able to escape directly from the core of a collapsing star, passing through layers of dense material that would trap or absorb other forms of radiation, which makes them extremely valuable for scientists trying to understand what happens inside these violent cosmic events. The most extraordinary feature of neutrinos is their ability to pass through almost anything, including entire planets, without being stopped, which means that Earth is constantly being penetrated by an enormous flow of neutrinos coming from all directions in space. These particles travel through solid rock, oceans, buildings, and human bodies with almost no interaction, making the entire planet effectively transparent to them. And this behavior is so extreme that neutrinos can pass through light years of solid lead without being absorbed or significantly scattered. This property makes neutrinos unique among known particles because almost everything else in the universe interacts with matter in some way, but neutrinos essentially ignore most of the physical barriers that stop or slow down other particles. To study these elusive particles, scientists have built some of the most advanced and unusual detectors in the world, designed specifically to capture the extremely rare occasions when a neutrino does interact with matter. One of the largest and most famous neutrino observatories is the IceCube Neutrino Observatory, located deep within the Antarctic ice, where thousands of optical sensors are embedded in a huge volume of frozen water beneath the surface. This location was chosen because the ice is extremely clear and stable, allowing scientists to detect faint flashes of light produced when a rare neutrino interaction occurs inside the ice. When a neutrino finally interacts with a molecule in the ice, it can produce a tiny burst of light called Cherenkov radiation, which is then detected by the sensors and recorded for analysis. Because neutrinos interact so rarely, IceCube must monitor an enormous volume of ice continuously to capture even a small number of events, making it one of the most sensitive particle detection systems ever created. Other neutrino experiments are located deep underground in mines or beneath mountains, where layers of rock shield detectors from cosmic rays and other background radiation that could interfere with measurements. These underground facilities often contain large tanks filled with ultra-pure liquids, such as water, heavy water, or liquid scintillators designed to produce detectable signals when a neutrino occasionally interacts with an atomic nucleus. The reason scientists go to such extreme lengths is because neutrino interactions are incredibly rare, and without shielding from other types of radiation, it would be almost impossible to distinguish neutrino signals from background noise. Scientists are deeply interested in neutrinos not only because they are difficult to detect, but also because they carry information from places that no other particles can escape from. Unlike light, which can be blocked, absorbed, or scattered by matter, neutrinos can travel directly from the core of a star or the center of a supernova explosion without being altered, which means they provide a direct view into regions of space that would otherwise remain completely hidden. This makes neutrinos extremely valuable as cosmic messengers because they can carry information about processes happening inside dense astrophysical objects that cannot be observed through traditional telescopes. Even more fascinating is the possibility that neutrinos could pass through environments that trap light completely, including regions near black holes, where gravity is so strong that even photons cannot escape once they cross the event horizon. While neutrinos would still be affected by gravity, their weak interactions with matter mean they could potentially escape regions of space that are otherwise invisible to conventional observation methods, making them one of the few known particles capable of providing indirect information about extreme gravitational environments. Because of these properties, scientists have begun to explore whether neutrinos could ever be used for communication purposes, although this idea remains highly experimental and extremely challenging due to the difficulty of producing and detecting neutrino beams. In theory, neutrino communication could allow messages to pass through solid planets or dense material without being blocked, since neutrinos do not interact strongly with matter. This means that a neutrino signal could travel directly through Earth from one side to the other without being absorbed, making it possible, in principle, to communicate between locations that are normally unreachable using traditional electromagnetic signals. However, because neutrinos are so difficult to detect and require extremely large and sensitive equipment to observe, building practical neutrino communication systems remains far beyond current technological capabilities. Despite these challenges, researchers have already conducted small-scale experiments attempting to send simple neutrino-based signals through Earth using particle accelerators and large detectors, demonstrating that controlled neutrino beams can be produced and detected under highly specialized conditions. These experiments represent the first steps toward understanding whether neutrinos could ever become a practical communication tool, although the energy requirements and technical limitations make widespread use extremely difficult with current technology. The scientific importance of neutrinos goes far beyond communication or detection because they are also fundamental to understanding the structure of the universe itself. Neutrinos played a major role in the early universe after the Big Bang, when the cosmos was extremely hot and dense, and large numbers of neutrinos were produced and released into space. These relic neutrinos still exist today as a faint background filling the universe, similar to the cosmic microwave background radiation, although they are far more difficult to detect due to their weak interactions. Modern cosmology suggests that neutrinos may also contribute to the total mass of the universe, although their exact contribution remains uncertain because of their extremely small mass. Even though each individual neutrino has very little mass, the enormous number of neutrinos in the universe means their total combined mass could still influence cosmic structure on large scales, affecting how galaxies form and evolve over time. The deeper scientists study neutrinos, the more they reveal how little of the universe is directly visible or easily accessible to human observation, because neutrinos represent just one example of particles that exist everywhere, but remain almost completely invisible to ordinary detection methods. Alongside dark matter and other unknown cosmic components, neutrinos highlight the fact that most of the universe operates in ways that are not directly observable through human senses or traditional instruments. And yet, despite their ghost-like behavior, neutrinos are not useless or irrelevant particles. They are essential parts of the universe's energy systems, constantly carrying information, energy, and momentum across vast distances, silently connecting distant cosmic events to regions of space far away. Every second, your body is being crossed by an unimaginable number of these particles without any effect you can feel, meaning that the universe is constantly interacting with you in ways that remain completely invisible to human perception. This hidden flow of neutrinos demonstrates that reality is far more complex than what human senses can directly detect, because beneath the visible world lies a constant stream of particles and forces passing through everything, shaping cosmic events while remaining almost entirely unseen. Extreme space environments that alter human biology. Space is not a calm or neutral environment for the human body, because every part of human biology evolved under very specific conditions on Earth, where gravity, atmosphere, radiation levels, temperature ranges, and magnetic protection all remained relatively stable for millions of years. And once humans leave that environment and enter space, the body begins changing in ways that are fast, measurable, and sometimes difficult to reverse. Inside a spacecraft or space station, the absence of normal gravity removes one of the most important forces shaping human biology. And this change begins affecting almost every system in the body within days. Because muscles that normally work constantly against Earth's gravity start receiving far less resistance, bones that depend on mechanical stress to maintain strength begin losing density, and fluids inside the body start shifting upward toward the head in ways that never happen on Earth under normal conditions. Astronauts returning from space often show clear physical differences compared to when they left Earth, not because space changes their identity or biology in a mysterious way, but because human bodies are extremely sensitive to environmental conditions and begin adapting quickly when those conditions change. One of the most significant changes that occurs in space is bone loss, because on Earth, bones are constantly under pressure from gravity, even when a person is simply standing still. And this pressure signals bone cells to maintain density and strength. But in microgravity environments such as the International Space Station, this constant load disappears, causing bones to gradually weaken over time. The body begins breaking down bone tissue faster than it rebuilds it, especially in weight-bearing areas like the legs, hips, and spine, leading to measurable decreases in bone density over long missions. This process is not immediate or dramatic in appearance, but it is scientifically well documented, and astronauts can lose a significant percentage of bone mass during extended stays in space if countermeasures such as exercise are not used. Alongside bone loss, muscle atrophy also occurs because muscles that are normally used to resist gravity no longer need to work as hard in microgravity, which causes them to shrink and weaken unless astronauts perform daily resistance training using specialized equipment designed to simulate gravitational load. Another major change involves fluid redistribution inside the body, because on Earth gravity pulls fluids such as blood and water toward the lower parts of the body. But in space, this downward pull is removed, causing fluids to shift toward the upper body and head, which leads to noticeable changes in facial appearance, increased pressure in the head, and sometimes even vision problems due to changes in eye shape and pressure around the optic nerve. Astronauts often report feeling as though their head is congested or swollen during the early stages of spaceflight, because the normal balance of fluid distribution has been disrupted. Over time, the body partially adapts to this new environment, but the effects remain an important challenge for long-term space travel. Vision problems in space are also linked to these fluid shifts and structural changes in the body, because increased pressure in the head can affect the shape of the eyeball and the functioning of the optic nerve, leading to a condition observed in some astronauts called space-associated neuroocular syndrome. This condition can cause temporary or sometimes longer-lasting changes in vision, highlighting how sensitive the human visual system is to environmental changes in pressure and fluid balance. Beyond physical changes, space also affects human cognition in ways that are still being studied, particularly through what astronauts describe as the overview effect, which is a psychological and neurological shift in perception experienced when viewing Earth from orbit, where the planet appears as a small, fragile sphere floating in darkness. While this effect is not fully understood at a neurological level, astronauts often report changes in how they perceive Earth, human systems, and interconnectedness. And researchers believe this may be linked to changes in sensory processing and brain activity caused by the space environment itself, combined with the emotional impact of seeing Earth from such a unique perspective. Even though this effect is often described in personal terms, scientists are still investigating whether long exposure to space conditions can alter neural pathways or cognitive processing in measurable ways. Space also interacts with the human body at the molecular level in ways that influence aging processes, because one of the most studied biological markers affected by space travel is telomere length, which refers to protective caps at the ends of chromosomes that naturally shorten over time as cells divide. In some studies involving astronauts, including long-duration missions, scientists observed unexpected changes in telomere length that suggested complex biological responses to space conditions, although the exact mechanisms are still being researched. Alongside telomere changes, exposure to space also increases oxidative stress in the body, which refers to cellular damage caused by highly reactive molecules, and this stress can affect proteins, DNA, and cell structures over time if not properly managed. Epigenetic changes have also been observed in astronauts, meaning that environmental conditions in space can influence how certain genes are expressed without changing the underlying genetic code itself, which shows that space environments can influence biology at multiple levels simultaneously. Because of these challenges, scientists are actively exploring advanced technologies to prepare humans for long-term space travel and potential colonization of other planets. And one of the most powerful tools in this research is genetic engineering through systems such as CRISPR, which allows precise editing of DNA. Researchers are studying whether it might be possible in the future to enhance human resistance to radiation, improve bone density retention, or modify cellular repair systems to better handle the stresses of space environments. Radiation is one of the most serious dangers in space because outside Earth's protective magnetic field, astronauts are exposed to higher levels of cosmic radiation, which can damage DNA and increase long-term health risks. So scientists are investigating whether genetic modifications could one day improve radiation resistance in human cells in controlled and ethical ways. Alongside genetic engineering, synthetic biology is also being explored as a way to support human survival in space environments, where engineered organs, modified blood systems, and enhanced oxygen efficiency could theoretically improve the ability of humans to function under extreme conditions. Researchers are studying artificial blood substitutes that might carry oxygen more efficiently or function under lower oxygen conditions, as well as engineered tissues that could repair damage more rapidly. While these technologies are still experimental, they represent a growing field of research aimed at understanding how human biology might be adapted for environments far beyond Earth. Another area of scientific interest involves sensory adaptation, including the possibility of enhancing or modifying human perception to better suit space environments. Some research has explored infrared perception in animals and how certain biological systems can detect wavelengths of light beyond normal human vision, leading scientists to investigate whether similar sensory extensions could ever be possible in humans through genetic modification or technological augmentation. In nature, many animals already possess sensory abilities that exceed human perception, such as seeing ultraviolet light or detecting magnetic fields, which demonstrates that biological systems can evolve or be adapted to perceive information beyond standard human senses. Space survival also depends on adapting to extreme environmental conditions over long periods, and scientists are considering what traits future humans might develop or be engineered to possess if long-term habitation in space or on other planets becomes a reality. One potential adaptation involves improved radiation resistance at the cellular level, where DNA repair mechanisms could become more efficient to handle constant exposure to cosmic radiation. Another possible adaptation involves enhanced oxygen storage or utilization, allowing the body to function more efficiently in low oxygen environments such as Mars or space habitats. Improved healing capabilities are also being studied, where faster tissue regeneration could reduce recovery time from injuries in environments where medical resources are limited. Altered sleep cycles may also become necessary because space environments often lack normal day-night cycles, which can disrupt circadian rhythms and affect hormone regulation, sleep quality, and cognitive performance. All of these biological changes, whether naturally observed in astronauts or theoretically explored through scientific research, highlight the fact that the human body is not fixed or unchangeable, but is instead highly responsive to environmental conditions, and space represents one of the most extreme environments that directly exposes this adaptability. When humans enter space, their bodies begin adjusting to new levels of gravity, radiation, and isolation. And these adjustments can reveal both the strengths and vulnerabilities of human biology in ways that are impossible to fully observe on Earth alone. What makes this field of study particularly important is that it connects directly to the future of human exploration beyond Earth. Because if humans are to live on the Moon, Mars, or in long-duration space missions, understanding how the body changes in space becomes essential for survival. Every known biological system in the human body evolved under Earth conditions, meaning that space introduces challenges that require either technological support, biological adaptation, or a combination of both. The study of space biology is therefore not just about observing changes in astronauts, but about understanding how life itself responds when removed from its original planetary environment and placed into conditions that push biological systems toward their limits. In this way, space becomes a natural laboratory for studying how flexible human biology truly is, because every mission reveals new information about how bones, muscles, fluids, cells, genes, and even cognition respond when gravity is reduced, radiation increases, and environmental stability disappears. These findings are shaping the development of future space technologies, medical systems, and potentially even human evolution if long-term space habitation becomes a reality. Black holes, the ultimate cosmic power source. Black holes are among the most extreme objects in the universe, not because they are simply dense or heavy, but because they represent a point where gravity becomes so strong that it completely reshapes space, time, and matter in ways that go far beyond normal planetary or stellar behavior. And to understand them properly, scientists had to first rethink what gravity itself means at the deepest level. The theoretical foundation of black holes begins with the work of Albert Einstein, whose general theory of relativity described gravity not as a simple pulling force, but as a curvature of space and time caused by mass and energy, meaning that any object with enough mass can bend the fabric of the universe around it. When Einstein published his equations in 1915, they provided a new mathematical framework for understanding gravity, but they also allowed for the possibility of extremely compact objects where mass could be compressed into such a small region that space-time itself would become infinitely curved. Shortly after Einstein published his theory, another physicist, Carl Schwarzschild, found a mathematical solution to Einstein's equations while serving in World War I. And this solution described what happens when mass is compressed into an extremely small volume. Schwarzschild's calculation showed that if enough mass is concentrated into a small enough space, there exists a boundary beyond which nothing, not even light, can escape. And this boundary is now known as the event horizon. At the time, this idea was purely theoretical and seemed too extreme to represent anything real in nature. But over time, scientists realized that Schwarzschild's solution matched what would happen to very massive stars at the end of their life cycles, when gravity overcomes all other forces holding matter apart. For many years, black holes remained mathematical predictions rather than physical objects because there was no direct observational evidence that they existed. And the idea of an object from which nothing could escape seemed so extreme that even Einstein himself was skeptical about whether nature would allow such objects to form. However, as astronomy advanced and telescopes became more powerful, indirect evidence began to emerge that pointed strongly toward the existence of black holes in space. Scientists studying stars in binary systems noticed cases where visible stars were orbiting invisible companions with extremely strong gravitational influence, and the behavior of surrounding gas and radiation suggested that something incredibly massive, but completely unseen, was affecting their motion. The first strong observational evidence for black holes came from systems where X-ray radiation was detected coming from regions of space where no visible star was present. And this radiation was later understood to come from extremely hot gas being pulled into a compact object with intense gravity. As gas falls toward a black hole, it accelerates to extremely high speeds and heats up due to friction and compression, forming a rotating structure called an accretion disk, which emits large amounts of X-rays before the material crosses the event horizon. These X-ray emissions became one of the primary ways scientists began identifying black hole candidates in space. Because even though the black hole itself cannot be seen, the behavior of matter around it reveals its presence. The structure of a black hole can be understood in three main parts, even though none of these parts can be observed directly in the usual sense, because the black hole itself does not emit light. The first and most important region is the event horizon, which is the boundary surrounding the black hole, where the escape velocity becomes equal to the speed of light, meaning that anything crossing this boundary, including light itself, cannot escape the gravitational pull. The event horizon is not a physical surface, but rather a mathematical boundary in space-time, marking the point where escape becomes impossible. And once any object crosses it, the direction toward the center becomes unavoidable, similar to how time itself begins to flow inward toward the singularity according to general relativity. Inside the event horizon lies the central region of the black hole, known as the singularity, where all the mass of the collapsed object is believed to be concentrated into an extremely small point or region of infinite density, according to classical physics equations. At the singularity, space-time curvature becomes infinitely large, meaning that the known laws of physics break down and cannot fully describe what happens there, which is why black holes are considered one of the greatest unresolved problems in modern physics. Scientists believe that a complete understanding of singularities will likely require a theory that combines general relativity with quantum mechanics, something that has not yet been achieved. Surrounding the black hole is the accretion disk, which is one of the most important observable features associated with black holes, because it is the region where matter from nearby stars, gas clouds, or other cosmic material is pulled into orbit before eventually falling into the event horizon. As this material spirals inward, it forms a rapidly rotating disk that heats up due to gravitational compression and friction between particles, reaching temperatures so extreme that it emits intense radiation across multiple wavelengths, including visible light, ultraviolet radiation, and powerful X-rays. This process makes accretion disks some of the brightest objects in the universe, even though the black hole itself remains completely invisible. The physics of accretion disks is extremely complex because matter behaves differently under such extreme gravitational conditions, where orbital speeds approach significant fractions of the speed of light and energy conversion becomes extremely efficient compared to most other astrophysical processes. As material spirals closer to the event horizon, it gains enormous kinetic energy, and a portion of this energy is converted into radiation that escapes into space, making black holes some of the most efficient natural energy conversion systems known in the universe. In some cases, jets of high-energy particles are also launched from regions near black holes, traveling at nearly the speed of light across vast distances and affecting the surrounding interstellar environment. The formation of black holes occurs when massive stars reach the end of their life cycle and can no longer support themselves against gravitational collapse, similar to neutron star formation, but on a larger scale where even neutron degeneracy pressure is not enough to stop the collapse. When a star significantly more massive than the Sun exhausts its nuclear fuel, the balance between outward pressure from fusion and inward gravitational force collapses, leading to a rapid implosion of the stellar core. If the remaining mass is large enough, the core continues collapsing beyond the point where neutron stars can form, resulting in a black hole. During this process, outer layers of the star are often ejected in a supernova explosion, while the core continues collapsing inward under its own gravity until it reaches the point where an event horizon forms. At this stage, the object becomes a black hole, and from that moment onward, the structure is defined entirely by its mass, spin, and charge according to the no-hair theorem in theoretical physics. This means that once a black hole forms, it loses almost all information about the original star, except for a few fundamental properties. Although black holes themselves cannot be observed directly, their effects on nearby objects provide strong evidence of their existence. One of the most powerful methods used to detect black holes involves observing the motion of stars orbiting invisible, massive objects, where the speed and shape of the orbits indicate the presence of extremely strong gravitational forces in a region that contains no visible matter. Another method involves detecting X-ray emissions from accretion disks, where infalling matter heats up to extreme temperatures before crossing the event horizon. These observations, combined with gravitational wave detections from black hole mergers, have confirmed that black holes are not theoretical constructs, but real physical objects that exist throughout the universe. Gravitational wave astronomy, in particular, has provided direct evidence of black hole collisions, where two black holes spiral toward each other and merge into a single, larger black hole, while releasing enormous amounts of energy in the form of ripples in space-time. These gravitational waves were first directly detected by the LIGO scientific collaboration, marking a major breakthrough in astrophysics because it confirmed predictions made by general relativity about how massive objects distort space-time when they accelerate or collide. These detections showed that black holes are not rare or isolated phenomena, but are actually common throughout the universe, forming through stellar evolution and merging over cosmic timescales. As scientists continue studying black holes, they are discovering that these objects are not just destructive endpoints of stellar evolution, but also play a crucial role in shaping galaxies and cosmic structures. Many galaxies, including our own Milky Way, contain massive black holes at their centers, which influence the motion of stars and gas clouds over enormous distances. These central black holes are far larger than stellar black holes and belong to a class known as supermassive black holes, which will be explored in detail in the next part of this documentary. For now, what remains clear is that black holes represent one of the most extreme expressions of gravity in the universe, where space is curved to its limits. Time behaves in unusual ways near the event horizon, and matter is compressed into conditions that push physics beyond its current understanding. They are not simply objects in space, but regions where the structure of reality itself becomes fundamentally different, and everything that falls into them disappears from observable universe in a way that challenges the limits of human knowledge about what matter, energy, and space truly are. Black holes, the ultimate cosmic power source. The universe contains regions where gravity becomes so strong that it stops behaving like anything familiar from everyday physics, and instead begins to reshape space, time, and energy in ways that only become visible when matter and light are pushed to their limits. And among these regions, the most extreme are the environments surrounding supermassive black holes, which exist at the centers of most large galaxies and act as enormous gravitational anchors controlling the motion of billions of stars over distances that stretch across tens of thousands of light years. These objects are not small or isolated phenomena formed from single stars, but instead are built up over long cosmic timescales through repeated mergers, continuous feeding of gas and dust, and possibly the collapse of extremely massive structures in the early universe, resulting in black holes that can contain masses equal to millions or even billions of suns compressed into a region smaller than our solar system. In the center of the Milky Way galaxy exists one such object known as Sagittarius A, a supermassive black hole that sits quietly at the heart of our galaxy, while influencing the orbits of nearby stars with a gravitational pull so strong that it provides one of the clearest pieces of evidence that these objects are not theoretical ideas, but real physical structures shaping the structure of galaxies themselves. The region around Sagittarius A has been studied for decades using increasingly powerful telescopes that track the motion of individual stars orbiting an invisible central mass. And what scientists observed is that these stars move at extremely high speeds, completing full orbits around an unseen object whose mass is estimated to be around 4 million times that of the Sun. Yet no visible light is emitted directly from the object itself, which strongly indicates that a compact supermassive black hole exists at the center of our galaxy. Observations made using infrared telescopes capable of seeing through dense clouds of interstellar dust have allowed astronomers to track stars such as S2 as they make full orbital loops around this invisible center, reaching speeds of several thousand kilometers per second at their closest approach, demonstrating that only an extremely dense gravitational source can explain their motion. These measurements provide some of the strongest indirect evidence for the existence of supermassive black holes and confirm that galaxies are not random collections of stars, but structured systems organized around central gravitational engines. As matter falls toward a supermassive black hole, it does not simply drop straight in, but instead forms a rotating accretion disk, where gas, dust, and stellar debris spiral inward at extremely high speeds, while being compressed and heated to enormous temperatures, producing radiation that can outshine entire galaxies in some cases. And this process plays an important role in shaping the observable universe, because active supermassive black holes can release more energy than all the stars in their host galaxy combined. In some galaxies, these active centers are visible as quasars, which are among the brightest objects in the universe, powered by continuous feeding of material into a supermassive black hole, where gravitational energy is converted into radiation with extreme efficiency. Even though the black hole itself remains invisible, the surrounding accretion disk becomes one of the most energetic regions in the universe, producing radiation across multiple wavelengths and sometimes launching jets of high-energy particles that extend far beyond the host galaxy into intergalactic space. Time behaves differently in the presence of such extreme gravity, and this effect becomes especially noticeable near supermassive black holes, where gravitational time dilation occurs due to the curvature of space-time predicted by general relativity, meaning that time itself flows at different rates depending on the strength of the gravitational field. Near the event horizon of a black hole, time passes more slowly compared to regions farther away, and this effect becomes more pronounced as one approaches the boundary, creating a situation where an outside observer would see objects falling toward a black hole appear to slow down and never fully cross the event horizon, while the infalling object itself experiences normal passage of time from its own perspective. This difference in time flow is not a theoretical idea, but a real physical effect that has been measured and confirmed in less extreme conditions within Earth's gravitational field. A practical example of gravitational time distortion can be observed in global navigation satellite systems, where precise time measurement is essential for accurate positioning on Earth, and satellites orbiting the planet experience slightly weaker gravity compared to observers on the surface, causing their onboard clocks to run at a different rate. Without correcting for this time difference predicted by Einstein's theory of relativity, GPS system would accumulate errors quickly and become inaccurate, demonstrating that gravitational time dilation is not just relevant near black holes, but is a measurable effect that must be accounted for in modern technology. If such effects can be detected and corrected in Earth orbit, then near supermassive black holes the difference in time flow becomes far more extreme, especially near the event horizon, where space-time curvature reaches its maximum observable strength. The environment around supermassive black holes also creates conditions where energy can be extracted in ways that are not possible in ordinary astrophysical systems. And one of the most important theoretical mechanisms for this process is known as the Penrose process, which describes how energy can be extracted from a rotating black hole under specific conditions involving the ergosphere, a region outside the event horizon, where space-time itself is dragged along with the rotation of the black hole. In this region, it becomes possible for particles to enter and split in such a way that one part falls into the black hole, while the other escapes with more energy than the original particle had, effectively extracting rotational energy from the black hole itself. This process shows that black holes are not only objects that consume energy and matter, but can also act as sources of usable energy under the right conditions, at least in theory. Another form of energy emission associated with black holes is Hawking radiation, a theoretical prediction developed by Stephen Hawking which suggests that black holes are not completely black, but instead emit a very small amount of radiation due to quantum effects near the event horizon, where particle-antiparticle pairs can form spontaneously, and one particle may fall into the black hole while the other escapes, resulting in a slow loss of mass over extremely long timescales. Although this radiation is extremely weak for large black holes such as supermassive ones, it becomes more significant for smaller black holes and represents one of the most important connections between quantum mechanics and gravity, showing that black holes slowly evaporate over time rather than lasting forever. The idea of using black holes as future energy sources emerges from combining these theoretical processes with advanced technological concepts, because the enormous energy output from accretion disks, jets, and rotational dynamics suggests that supermassive black holes could represent some of the most powerful natural energy systems in the universe. In principle, if a civilization could safely access regions near a black hole and control the flow of matter into its accretion disk, it might be possible to extract vast amounts of energy far beyond anything achievable through conventional stellar or planetary systems. The efficiency of energy conversion near black holes already exceeds nuclear fusion in many cases, since matter falling into a black hole can release a significant fraction of its mass energy as radiation before crossing the event horizon. The challenge, however, lies in the extreme environmental hazards present near these objects, including intense radiation from accretion disks, high-energy particle jets, and strong tidal forces that can stretch and compress matter in dangerous ways, meaning that any attempt to use black holes as power sources would require advanced control systems capable of managing conditions far beyond current human technology. Even so, the physics suggests that black holes are not simply destructive endpoints of stellar evolution, but also potential reservoirs of usable energy on cosmic scales, especially when considering rotating black holes, where additional energy extraction mechanisms become possible through interactions with the ergosphere. Black holes, the ultimate cosmic power source. In the far future of science and technology, black holes are not just seen as destructive endpoints of collapsed stars, but as potential tools that an extremely advanced civilization might learn to use, control, or at least engineer around, because the energy scales, gravitational forces, and time distortions around them are so extreme that they represent levels of physics far beyond anything humanity currently uses. And to understand this idea properly, scientists often connect it to the Kardashev scale, which is a way of classifying civilizations based on how much energy they can control in the universe. On this scale, a Type 1 civilization controls the energy of its home planet, a Type 2 civilization controls the energy of its star, and a Type 3 civilization controls the energy of its entire galaxy, meaning that a civilization at this level would have access to energy sources far beyond nuclear fusion or stellar power. And in that context, supermassive black holes become one of the most powerful energy systems that could possibly exist, since they already release enormous amounts of energy naturally through accretion disks, relativistic jets, and gravitational interactions. At a Type 2 or Type 3 level of development, civilizations might begin to treat black holes not as dangers to avoid, but as engineered systems to extract energy from, leading to theoretical concepts such as black hole engines, where matter is deliberately fed into a controlled accretion disk around a rotating black hole in order to convert gravitational potential energy into radiation that can be captured and used. And because the efficiency of energy conversion near a black hole is significantly higher than nuclear fusion, such systems would represent energy sources of almost unimaginable scale. In some theoretical models, Rotating black holes could be used in configurations where their spin energy is gradually extracted through processes similar to the Penrose mechanism, allowing a civilization to tap into the rotational energy of a black hole over extremely long timescales, effectively turning it into a cosmic power generator that slowly converts mass and rotation into usable energy. More advanced theoretical concepts extend this idea further into relativistic civilizations, where technological systems operate in extreme gravitational environments and possibly take advantage of relativistic effects near black holes to perform computations or energy processing at scales and speeds that would not be possible in normal space. In such environments, time dilation near a black hole could allow processes to run at different effective speeds depending on gravitational position, meaning that parts of a computational system located closer to a black hole could experience time more slowly relative to distant observers, effectively creating time-separated processing layers within a single system. Although such ideas remain highly theoretical and depend on physics that is not yet fully understood or technologically accessible. Even if civilizations could not directly control black holes, they might still attempt to survive and operate near them under carefully controlled conditions, which leads to the question of what it would mean to survive near a black hole and what regions around these objects might remain stable enough for long-term orbital structures or scientific operations. Contrary to popular imagination, black holes do not automatically pull everything from enormous distances into them, because objects can orbit a black hole safely at certain distances if their motion balances gravitational pull, much like planets orbit stars, meaning that stable orbit possibilities do exist around black holes depending on distance, velocity, and the mass of the black hole itself. Around supermassive black holes, the gravitational gradient near certain regions can be relatively gentle compared to smaller black holes, allowing stable orbits at distances where tidal forces are not immediately destructive, which means that, in theory, structures or spacecraft could exist in orbit around such objects if they are placed carefully far enough from the event horizon. However, even in stable orbital regions, the environment near black holes presents severe challenges due to tidal forces, which arise because gravity changes significantly across small distances when approaching a massive object, and these tidal differences can stretch objects along one axis while compressing them along another, creating stress that increases dramatically as one gets closer to the event horizon. In smaller black holes, tidal forces near the event horizon become so strong that any object crossing too close would be stretched into long, thin streams of matter in a process sometimes informally described as spaghettification. But in supermassive black holes, the event horizon is much larger, meaning tidal forces at the boundary can be significantly weaker, allowing a theoretical tidal survival zone where an object could cross the event horizon without being immediately torn apart, even though escape would still be impossible after crossing that boundary. Another major challenge near black holes is radiation danger from accretion disks, because matter falling into a black hole heats up to extreme temperatures and emits high levels of X-rays and gamma rays, which are forms of high-energy radiation that can damage biological tissue and electronic systems if not properly shielded. In active black hole systems, where accretion disks are large and continuously fed with matter, the surrounding environment can become extremely hostile due to constant radiation exposure combined with high-energy particle jets that can extend thousands of light years into space, making close approach extremely dangerous for any form of known technology or biology. Even at safer orbital distances, long-term exposure to such radiation would require advanced shielding systems far beyond current human engineering capabilities. Despite these dangers, theoretical physics allows for interesting ideas about how black hole environments could be used for extremely advanced technological applications, especially when considering how gravity, time, and energy behave near these objects, which leads to several superpower-like possibilities when interpreted through a purely scientific lens. One of the most significant effects is time manipulation through gravitational time dilation, where time flows at different rates depending on proximity to the black hole, meaning that a system closer to the event horizon would experience time passing more slowly compared to one farther away, creating natural time differences that could be used for synchronization, computation, or energy management in hypothetical advanced technologies. Another major possibility is near limitless energy access, because black holes represent some of the most efficient energy conversion environments in the universe, where matter falling into them can release a large fraction of its mass energy as radiation before crossing the event horizon. And in rotating black holes, additional energy can be extracted from spin, meaning that in theory, a carefully engineered system could tap into multiple layers of energy production simultaneously, combining accretion disk radiation, relativistic jet energy, and rotational energy extraction into a single, extremely powerful energy source. This makes black holes one of the few known natural objects that could theoretically support energy demands far beyond what stars alone could provide in advanced civilizations. A further theoretical possibility involves extreme computational power, because the combination of gravitational time dilation and high-energy environments could allow computational systems to operate in ways that are fundamentally different from those on Earth, where time differences between regions near and far from a black hole could be used to structure layered computation processes, potentially allowing certain calculations to occur in effectively different timeframes depending on gravitational position. While this remains speculative, it demonstrates how black hole environments push the boundaries of what is considered possible in physics, especially when considering how information, energy, and time behave under extreme gravitational curvature. Alien biology: what evolution in space could really create? Life on Earth shows very clearly that evolution is not a fixed process that produces the same results everywhere, but instead it is a direct response to the environment in which it develops, meaning that every biological trait seen in animals, plants, and microorganisms is shaped by pressure from surroundings such as temperature, pressure, radiation, available energy sources, and competition for survival. And when these environmental conditions change drastically, the direction of evolution can also change in equally drastic ways. On Earth, some of the most extreme environments already show how far biology can stretch under unusual conditions, such as the deep ocean where sunlight never reaches, and pressure is so strong that it can crush ordinary structures. Yet life still exists in forms that appear completely alien compared to surface organisms. In these deep-sea environments, creatures have evolved to survive in complete darkness by developing entirely different biological strategies, including enhanced sensory systems that rely on pressure, vibration, and chemical detection rather than vision. And in some cases, organisms produce their own light through bioluminescence, which allows them to communicate, hunt, or camouflage themselves in an environment where sunlight does not exist at all. The presence of electric animals on Earth further demonstrates how evolution can produce biological abilities that resemble natural versions of what might be considered extraordinary powers, such as the electric eel, which can generate strong electrical discharges through specialized cells that store and release electrical energy to stun prey or defend against predators. This biological electricity is not magical or supernatural, but instead comes from highly specialized adaptations of muscle and nerve cells that evolved to serve specific survival functions, showing that nature can develop internal electrical systems when environmental pressures favor such traits. Similarly, some species have evolved echolocation, such as bats and certain marine mammals, where sound waves are used to navigate and detect objects in complete darkness or murky water, effectively allowing these animals to see through sound by interpreting echoes that bounce back from surrounding objects. Other forms of biological sensing also exist in nature, such as electrolocation, where certain aquatic species can detect weak electric fields produced by other organisms, allowing them to locate prey or navigate in environments where vision is limited, and infrared sensing, where some snakes can detect heat signatures emitted by warm-blooded animals, giving them a form of thermal vision that allows them to hunt in complete darkness. These abilities demonstrate that biological systems are capable of evolving sensory inputs far beyond human perception when environmental conditions create strong survival advantages for such traits, and they provide real examples of how life can develop functions that might appear superhuman from a human perspective, but are entirely natural within their ecological context. When considering life in space or on other worlds, scientists examine environments that are dramatically different from Earth, including icy moons such as Europa, which is believed to have a vast ocean beneath its frozen surface, where conditions may include extreme cold, high pressure, and complete absence of sunlight. Yet internal heating from tidal forces could create energy sources capable of supporting life in forms very different from those on Earth. In such environments, organisms might rely on chemical energy sources rather than sunlight, similar to extremophiles found near hydrothermal vents on Earth, where life thrives without sunlight by using chemical reactions involving minerals and gases released from the ocean floor. Another major example is Titan, one of Saturn's moons, which has a thick atmosphere and lakes of liquid methane and ethane on its surface, creating a completely different chemical environment where life, if it exists, might not be based on water chemistry at all, but instead on hydrocarbons that behave as solvents under extremely low temperatures. Ocean worlds beyond Earth may also exist throughout the galaxy, where subsurface oceans beneath icy crusts could provide stable environments protected from radiation, allowing life to develop in isolated aquatic systems over long periods of time. And these environments could produce entirely different evolutionary outcomes depending on available energy sources, chemical compositions, and environmental stability. In some speculative scientific models, methane-based life is considered as a possibility in extremely cold environments where chemical reactions could occur in liquids other than water, although no direct evidence of such life has been found. And current research remains focused on understanding whether alternative biochemistry could support self-replicating systems similar to biological life as it is currently known. One of the major questions in astrobiology involves whether life must always be based on carbon chemistry, which is the foundation of all known life on Earth, or whether alternative elements such as silicon could potentially form the basis of biological systems under different environmental conditions. Carbon is extremely versatile because it can form stable bonds with many different elements and create complex molecules necessary for life. But silicon, which sits in the same group in the periodic table, also has the ability to form complex structures, although its chemistry behaves differently, especially in the presence of oxygen, where it tends to form solid compounds rather than flexible molecular chains. This has led scientists to debate whether silicon-based life could exist in environments with different temperatures, pressures, or chemical compositions, although most current evidence suggests that carbon remains the most suitable element for supporting complex biological systems. Another fascinating concept in biology involves the possibility of hive minds or distributed intelligence systems, where multiple organisms function as part of a larger coordinated structure rather than operating as fully independent individuals. And this already exists in nature in various forms, such as ant colonies, beehives, and certain slime molds, where simple individual units work together to produce complex collective behavior that appears highly organized. In these systems, communication between individuals allows the group to function as a single adaptive system, responding to environmental changes through distributed decision-making processes rather than centralized control. And this raises interesting possibilities for how intelligence could evolve under different environmental pressures, especially in space environments where cooperation might be essential for survival. Some research in biology and neuroscience has explored whether forms of collective intelligence could become more advanced under certain conditions, potentially leading to systems where neural networks extend beyond single organisms into larger interconnected biological structures, although such ideas remain speculative and are not supported by direct evidence in current known life forms. However, certain biological systems already show limited forms of network communication, where chemical signals, electrical impulses, or even light-based signals coordinate behavior across groups of organisms, suggesting that nature already contains early examples of distributed information processing. The question of whether space could produce telepathy-like systems is often raised in popular discussions. But in scientific terms, this concept is usually explored through the study of electromagnetic communication and quantum biology, where researchers investigate whether biological systems can use weak electromagnetic fields for signaling or whether quantum effects play any role in biological processes at microscopic levels. Some animals already use electromagnetic sensing for navigation or detection, and certain studies suggest that weak electrical or magnetic fields could influence biological activity in subtle ways, although there is no evidence supporting direct mind-to-mind communication as imagined in fiction. Instead, scientific research focuses on understanding how biological systems process information through physical signals, such as electricity, chemistry, and light, which are already fundamental to all known life processes. Even though true telepathy remains outside scientific support, the idea of enhanced biological communication systems is still grounded in real biology when considering how evolution might operate under extreme conditions. In environments where survival depends on rapid coordination or adaptation, organisms might evolve more efficient signaling methods, potentially including faster electrical communication, improved chemical signaling, or more sensitive environmental detection systems that allow groups of organisms to respond collectively to external changes. Humanity is already connected to space because the atoms in the human body were formed inside ancient stars that exploded long before Earth existed. Elements like carbon, oxygen, iron, and calcium were created in these stellar events and later became the material that formed planets and life. Because of this, life on Earth is made from recycled cosmic material. What people call superpowers in biology are usually extreme adaptations shaped by environment. These traits always come with trade-offs in energy use, structure, and survival limits. Evolution cannot improve one ability without affecting others, which is why nature produces specialized survival traits rather than unlimited powers. In the future, human change may come from space exploration, genetic engineering, cybernetic upgrades, and neural interfaces. These technologies could enhance strength, perception, and survival in harsh environments. But even with these changes, biology will still follow physical limits. The universe does not create superheroes, it creates survivors.